Minna. I hope you can see me and my slides. I unfortunately can't see you, so I'm sure many of you are familiar with this experience of just talking into the void of the internet. So yeah, please do interrupt me, or Minna, perhaps I'll leave you to be the moderator to sort of, if there are any questions throughout the talk, to just interrupt me. So yeah, as Minna said, thank you for the very generous introduction. And my name is Daniela Massiceti, and I'm a senior researcher at Microsoft Research. I'm very sad that I can't be there at CVPR in person this year. I'm based in Sydney, and so it's a long flight. But I'm hoping in future years I will be able to attend. But thank you very much for having me. Today's talk, I'd like to share a little bit about some of our recent results, which show how few-shot approaches can be used to make large multimodal models more inclusive. So just to set the scene a little bit, one of the main questions that has driven my research over the years is, how do we ensure that AI technologies are going to work for the long tail of users? That is, how are we going to ensure that an AI system will work equally well for me as it does for you, as it does for someone with a disability, as it does for someone living in the global south? And this is a very hard problem. And indeed, we've already seen several examples of where these AI models don't work for these marginalized communities or these people in the tails of the distribution. We've seen work that has shown facial recognition systems not working as reliably for people of color, particularly women of color. We've seen that sentences that describe people with disabilities are more likely to be flagged as toxic compared to sentences that describe people without disabilities. And we've also seen, I think, many examples of how generative models, text-to-image models like DALL-E, have these deeply encoded social biases. So here the prompt was to generate an image of an intelligent person, and the majority of the resulting images are kind of white male individuals. And so, as we're seeing now this rapidly moving space of generative AI, and all the places it is being deployed, I think it will become even more important for us to understand quite deeply where models are not working for marginalized communities, so that we can ensure that these technologies don't go on to further marginalize or exacerbate the divide for these communities. And so today's talk will address some of these aspects. Specifically, it'll be broken down into 3 sections. So first, we'll ask the question, are today's multimodal models inclusive? The short answer is that they're not. As I've already discussed, there's a wealth of literature building up to support this claim for a wide set of marginalized communities. But in this specific talk, I will be sharing some new findings from our team for one specific community, the blind and low vision community. We'll then next ask the question, okay, so if current models are not inclusive, then what can we do to fix them? And specifically, I will present some results around how we can leverage a few-shot learning approach to get models to learn rare concepts, rare visual concepts, and this is showing quite a lot of promise. And then finally, I'll discuss what the path forwards might look like toward building more inclusive models. And I'll specifically bring up some of the questions that are currently top of mind for our team at MSR. Okay, so let's jump right in. So today's AI models, as we know, hold incredible potential for many people, but in particular, the blind and low vision community, from text recognition to product identification to question answering. And apps like Microsoft's Seeing AI have already deployed some AI features, but I think as we look at really the range of tasks that users who are blind need help with, most of them remain out of scope for most current day models. And I think we see this most clearly in the fact that most users still prefer human assistance in getting their tasks done. So they'll often either call on someone who's physically there, or they'll dial into an app like Be My Eyes, which connects a blind person with a remote sighted assistant via a video call. But of course, with the introduction of these multimodal models and the massive leaps that we've seen with them over the last year, could we ask the question, could this provide a fully automated alternative to this? And I think we see a real hope from both the technology world and the blind community, perhaps most visible in this very public partnership between OpenAI and Be My Eyes. But despite their potential, these multimodal models have not been systematically evaluated in any way on data from blind and low vision users. And we suspect that this data may pose challenges to these models because the data is out of distribution in a number of ways. So, for example, blind users use a range of quite specific assistive objects, which are not commonly used by everyone. They're more likely to capture images with quality issues, things like blur, variation in lighting, occlusion. They are also more likely to make use of non-visual vocabulary. So, for example, describing things by their physical or tactile properties rather than their visual properties. And so our work basically set out to remedy this. Specifically, we evaluated 25 variants of CLIP on data from blind and low vision users. And the reason for selecting CLIP is that it is probably one of the most widely used multimodal models. It has, as it currently stands, over 15,000 citations and 75 million plus downloads on Hugging Face. And it's used not only as a standalone model, but I'm sure, as you're all aware, also as a component in many other downstream systems. And so we wanted to test these CLIP variants on data from blind and low vision users, specifically the Orbit dataset and the VisWiz classification dataset, both of which were collected by blind users through real-world assistive technologies. And then we inspected CLIP's performance not only on a zero-shot image classification task directly, but we also looked at its performance, the performance of downstream models that use CLIP as a component, which I mentioned before. And so before I start diving into the details, which you'll find in our CVPR paper, which I've linked at the bottom of the slide here, I wanted to sort of pop up or zoom out and just share our top 3 findings with you. So if these are the only 3 findings you remember and you've overloaded with talks from today, then these 3 findings are the ones that will hopefully stay with you. So first, we basically confirm that CLIP underperforms on data captured by blind and low vision users on a direct zero-shot image classification task. The second finding was that these disparities trickle down into models that use CLIP as a component. And our third finding is that these disparities stem from the fact that disability content is significantly underrepresented in the datasets that are used to train these models. And so I'll now dive into each of these findings in a bit more detail. So starting off with our first finding, CLIP underperforms on data captured by blind and low vision users. As I mentioned, we specifically looked at this question through a zero-shot image classification task. And we did this because it provides almost a worst-case estimate for how well CLIP will serve downstream assistive applications if used out of the box. So how zero-shot classification works, for those of you who are perhaps not familiar, basically we give CLIP a set, we give CLIP a set of object classes and a test image, and then we ask it to select which class is present in this image without any fine-tuning on these object classes. So what this looks like in practice is that we would have a data set of objects. We would randomly sample n objects from that data set. We would then sample, say, m test images for each of those objects. We would feed the n object labels through CLIP's text encoder to get n text embeddings. And we would then pass let's say, one test image through CLIP's vision encoder to get its image embedding. And we can then compute the cosine similarity between these 2 sets of embeddings to get n similarity values. And the object label with the highest similarity value is then taken to be CLIP's prediction for the object in that image. And we can kind of loop through all of these m test images to get predictions for all of them. And we actually repeat this process in our experiments 50 times, each time sampling a different set of n objects and a different set of m test images for those objects. And we then report the average accuracy over all of the images that we tested. And as I mentioned, we do this for 25 variants of CLIP. You're probably most familiar with the OpenAI variant of CLIP. This was trained on a dataset called WIT, or WIT. But since its release, there have been many other open source variants of CLIP that have been trained, and they spanned not only the size of the vision and text encoders, but also the data sets that were used to pre-train them. And so we looked at all of these. So within this experimental setup, our goal was to assess CLIP's performance along 3 dimensions that are relevant to the blind and low vision community. Referencing, and you'll see they reference the aspects I mentioned before. So first, image content. We basically look to see how well does CLIP recognize assistive objects like guide canes and liquid level sensors. Second, image quality. How robust is CLIP to the quality variations that typically are present in images captured by blind users, for example, blur and occlusion. And then finally, textual content. So how sensitive is CLIP to the language that a blind user would typically use? For example, can it recognize an object if you describe it by its tactile adjective, like, a plastic mug, versus a visual adjective like a yellow mug? And so I'll step through now some of our key results in each of these dimensions. Starting with image content. So to study this, we manually labeled the objects in the orbit dataset as either a disability object. So these are objects that can help a person who's blind, like a dog lead that might be used with a guide dog. Exclusive disability objects. So these are objects that would be exclusively used by someone who's blind, like a braille display or a guide cane. And then finally, non-disability objects, which are just objects used by everyone. So for example, a TV remote. And we then ran our zero-shot classification setup and then analyzed how CLIP performed, the sort of average accuracy of CLIP for each of these 3 object groups. And basically our results showed that the disability objects have a zero-shot accuracy that is 21 percentage points lower than non-disability objects. And this gap widens to 25 percentage points when we measure that against the exclusive disability objects. And these disparities were reported on what is called the clean split of the orbit dataset, which are basically just very simple images that show just a single object on a clear surface with no other things around. So really sort of the simplest setting that you can get. And actually, we see that these disparities or these accuracy gaps widen by a further 3 or 4 percentage points when we put, when these objects appear in more realistic cluttered images, which is, I guess, more like what users will actually encounter in the real world. Our first natural question was, okay, well, does this gap close if we just kind of give CLIP more pre-training data? But actually, we find that it, in general, as we can see from this trend here, the accuracy does generally increase as CLIP's pre-training data set size increases. But as you can see, the delta here, so this is the difference between the orange line, which are the non-disability objects, and this purple and green line, which are the exclusive disability and just pure disability objects. This delta doesn't really change. This stays pretty constant. And we saw similar trends for when we looked at if architecture size kind of improves this gap. And so this kind of gives us this early suggestion that perhaps just web crawling more data or making models bigger, which are sort of the current strategies to sort of fixing the problem, may not be enough to equalize performance for disability objects. Moving now into the second dimension of image quality. So as I mentioned before, we know images captured by users who are blind have more variable quality. And so we wanted to understand how robust CLIP was to those variations. And luckily, the Orbit, Clean, and the VisWiz classification datasets are actually annotated with several of these quality issues, including blur, lighting issues like over and under exposure, framing issues, occlusion issues, and camera viewpoint issues. And so we were able to leverage these annotations in our analyses. We used logistic regression, which is a common tool in hypothesis testing to estimate the marginal effect of each of these quality issues on model accuracy. So specifically, we model P as the probability that CLIP correctly identifies the ground truth object, with 1 being correct and 0 otherwise. And then we had this vector X of Booleans indicating which of the quality issues were present in that particular image. And we actually also incorporated this D variable, also a Boolean, which would indicate if the ground truth object was a disability object or not, because we were interested in understanding if quality issues kind of compound or get worse if they happen or co-occur with a disability object. And then our goal was to then estimate these alpha and beta coefficients. So these are the marginal effects, and we did so with maximum likelihood. So I won't go into more mathematical detail than that. But basically, if we look at these results here, we see that blur, viewpoint, occlusion, and lighting issues all have large negative marginal effects on the model accuracy with a high statistical significance. And so just in terms of how to sort of read this plot, each dot here represents a particular clip variant. And its position on the graph, so on the y-axis, represents the size, or I guess the amplitude of its marginal effect, with color representing then its statistical significance, with dark blue being a very high statistical significance, or a p-value of under 0.01. And we can see that these quality issues have an negative effect, not only on the orbit dataset, but also on the VisWis classification dataset. We also see, if we look at this, this very negative column here, we also see that the marginal effect of the image containing a disability object is large, negative, and statistically significant. And this basically mirrors the results that we saw in the previous section, those accuracy gaps between disability and non-disability objects. But interestingly, when we co-occur a disability object with the quality issues, we actually see that disability objects are impacted no worse than non-disability objects. So that's a good finding from these results. And then moving on to our final dimension of textual content, we wanted to understand how CLIP performs on the range of language used by people who are blind or low vision. So for example, as I mentioned, blind users commonly use tactile words rather than visual words to describe their objects. And so to give you a very obvious example of this, a user who is blind might describe this image as, their leather boot rather than their brown boot. Or, this is their denim wallet rather than their black wallet. And so in our work, we studied this particular instantiation. How well can CLIP recognize objects if they are described by their color versus their material? And so to study this, we manually labeled each object in the orbit dataset with its color and material. And we selected these from a predefined list of 20 colors and 23 materials. And we created basically 4 different text prompts for each of the objects. So the first, we just consider a lower bound. So this is just the object name. This is the text label we were giving CLIP when we were doing just the standard zero-shot classification. The second is a material prompt. So this is when we combine the object's name with its material. The third is a color prompt. So that's when we combine the color with the object name. And then finally, an upper bound prompt, which includes both the object's material, its color, and the object name. And we basically give these to CLIP's text encoder alongside a test image of that object. And we do this for 100 randomly sampled images for each object, and then compute the CLIP score between the image embedding and each of these different textual prompts. Now, the CLIP score, for those of you who are not familiar, is a metric used to measure how similar two embeddings are or how aligned they are. It's basically a scaled version of the cosine similarity. And what we see here is that the color prompts have the highest CLIP score, while the material prompts have the lowest CLIP score. And interestingly, this upper bound prompt, so the prompt that included both the color and the material, has a lower CLIP score than just the color prompt alone. So this suggests that adding in the material is actually harming the embedding's alignment. And this is really quite unexpected. I think we hypothesized that this upper bound prompt would have the highest CLIP score because in some sense we're providing the most detail about the object's appearance. But it seems that color really dominates and material sort of detracts from that performance. The CLIP scores, however, are only looking at the embedding space, as we know, and so we also wanted to quantify the impact of these sort of color versus material prompts on the kind of ultimate classifier accuracy. And so we did this using a standard, again, zero-shot setup, instead now using these textual prompts rather than just the object name. And we basically see that across all of the variants of CLIP, CLIP classifies objects around 7 percentage points more accurately when the objects are described by their color. So these are the orange bars, rather than their material, which are shown by the green bars. And so again, we have this, this suggestion that, CLIP may actually not perform that well for blind users if they are describing their objects by their material. And there's the potential that this might extend to other kinds of tactile-based descriptions as well. So that wraps up a very brief look at some of our results from our first finding around what kinds of performance disparities we're seeing on data from blind and low vision users. That section was by far the deepest dive, so if you're still with me, that's great news. The following sections will hopefully be much lighter weight, and maybe I'll pause here for any questions before I dive into this next finding.
So is there any questions? Okay, so you can continue, Daniela. Thank you. Do you hear us?
Yeah. Yes.
So no questions so far. You can continue to the next part. Thank you.
Yeah, sounds good. So yeah, now onto the second finding. So earlier I mentioned that CLIP is quite widely used as a standalone model, as we know, but it's also used as a component in many other downstream models. And so we wanted to quantify if these disparities are actually trickling down to these downstream models that use CLIP under the hood. And so we studied, to answer this, we looked at 3 models that use CLIP as a component. OWL-VIT, which is an object detection model that uses a CLIP vision encoder. CLIP-SEG, which is a CLIP-based semantic segmentation model. And then DALI-2, which is a text-to-image model that also uses a CLIP vision encoder. And we studied these 3 models on a set of carefully selected images, a set of around 180 images. And so because this was a relatively small set of images, we were actually able to manually evaluate all the predictions that came from each of the models. And so I'd like to just share a couple of our more qualitative results from across these 3 models. So our study of OWL-VIT showed that it detected disability objects less consistently and less confidently than non-disability objects. So if we look at this example over here, for instance, or maybe actually rather these guide cane examples, we basically saw the model oscillating for, basically between detecting the correct object in one image and then the incorrect object in another image for the same object. And often the confidence was actually higher when it detected the wrong object. And we see this for both examples of the guide cane here. So here it's detecting the guide cane correctly, but then it's detecting this kind of door jamb in the second image, and it's pretty much the same object with a very similar setting. And so you can imagine how much of a negative effect or negative user experience this would be for someone who's actually using an object detection app to help find one of their disability objects. For our second model, CLIP-SEG, we found that it is more likely to segment the wrong object if that object was a disability object, and this was especially the case in cluttered scenes. So here we mark the ground truth object with a blue bounding box. Sorry, it's very light blue bounding box. But as we see here, for almost all of these images, CLIP-SEG doesn't segment the correct object. And quantitatively, we saw this happening on average around 2 times more often for disability objects than non-disability objects in these cluttered scenes. And then finally for DALI-2, I think these are some of my favorite images from the paper because they really visually depict kind of these models failing. Basically, we saw that whenever we prompted DALI-2 to generate a disability object, it failed quite miserably. So either it defaulted to a more common object. So here, for example, we asked it for a guide cane, and it gave us kind of examples of walking sticks, although some of them are quite funny looking walking sticks. Or it fabricated the objects completely. So here we asked for a Braille keyboard, and basically it gave us, as you see here, just lots and lots of random white dots. And in comparison, I haven't shown these examples here, but DALL-E generated very high quality and realistic images for almost all of the non-disability objects that we tested it on. And so we really saw that across all of these three downstream models, they are struggling with disability content, perhaps hinting that CLIP, which itself struggles with this content, is playing a role here. And then moving on to our third finding, disability content is underrepresented in large-scale public data sets. I think given the results I've presented so far, you've probably already got a good sense for where the issues may stem from, and that is indeed from the data that is used to pre-train CLIP. And so we wanted to confirm if this was indeed the case. We sort of had the same hypothesis. And so we wanted to sort of explicitly quantify, well, how prevalent is disability content in these data sets? So as I mentioned earlier, OpenAI's version of CLIP is trained on a data set called WIT or WIT, but this data set is unfortunately closed source. So we instead examined LION 4 million, LION 2 billion, and DataComp 1 billion. These data sets were used to pre-train some of the other CLIP variants that we studied, the open source CLIP variants. We used very simple NLP processing techniques to actually quantify the disability content. Specifically, we chose to analyze the captions of these data sets, which was more computationally tenable than actually looking at the images. Even our caption processing experiments took about 5 days to run on such huge data. And basically, we started off by first extracting all the physical noun phrases from these captions. So, for example, a yellow mug would be an example of a noun phrase. And we did this using a combination of speech tagging and the WordNet object hierarchy. And then once we had this set of noun phrases, we basically we counted how frequently specific disability things were mentioned in these noun phrases using some string matching after some simple pre-processing. So I'll present to you sort of two sets of results from these analyses. The first type of disability content we looked for are naturally disability object names, and we found that they occurred 16 to 17 times less frequently than non-disability objects across all three of the data sets. And the second type of disability content we looked for were materials versus colors, echoing the results that we looked at earlier. And again, here we find that materials appear 4 times less frequently on average than colors across all three of these data sets. And so, yeah, I think both of these analyses really confirmed or provided, some confirmation of the underlying source of the performance disparities we saw in our earlier results. So, yeah, that kind of wraps up this first section of the talk. Are today's multimodal models inclusive? And I think, our specific piece of the work that I presented here kind of adds another data point to the literature around how these models are not necessarily working well, not inclusive of particular marginalized communities. But up until now, all I've spoken about are the problems, and that, of course, doesn't solve very much. And so our next question was, well, what can we do to fix some of this? What can we do to make these models more inclusive? So you will recall the accuracy gaps I presented earlier. We saw these significant differences in accuracy in how well CLIP can recognize disability objects versus non-disability objects. And so our goal was to explore strategies that could potentially reduce this gap and take a step toward making models like CLIP more inclusive of content that is important to marginalized communities. So again, we explored this through the lens of the blind and low vision community, but I think the strategies we are investigating here have the potential to be extended to other kinds of content for other marginalized communities as well. So specifically, we investigated 3 mitigation strategies. As a baseline, we just had the vanilla zero-shot setting. So here, CLIP is given a photo of an object, and in this case, a guide cane, along with the text caption, a photo of a guide cane. and Clip is then asked to predict it or classify it from a set of n other objects. And this is the setting, as we know from before, which leads to those large accuracy gaps between disability and non-disability objects. But we know there's a wealth of work that has been done to improve Clip's recognition performance, especially on more difficult or rare objects. And so the first approach or strategy we looked at or we compared to was to add an LLM into the mix. So specifically, we prompted GPT-4 with what are the useful features for distinguishing a guide cane in a photo. And this basically gave us a much richer description of the appearance of the object, which we then fed to Clip instead of just that very simple text prompt, along with the image to get a prediction. Our second strategy followed a similar vein. We considered another well-cited approach that does a similar thing, except just with a different prompt. So it asks, what does a guide cane look like? So instead giving us this sort of rich textual description of some of the features of what a guide cane might look like. And then our third and final approach was a few shot setting or a few shot approach, where we actually gave Clip a few actual images of a guide cane. So these are the few shots. And these images were actually collected by users who are blind. So very kind of community-driven data collection. Specifically, we used ProtoNets, which is a very widely successful and actually quite simple few-shot approach. And basically what we do is we feed these K images for each of the N classes into Clip's vision encoder, and we compute an average embedding for each of these classes. And then when we have some new test image, we then can classify that by passing it through Clip's vision encoder, getting its visual embedding, and then computing the Euclidean distance and the between this embedding and the class-wise embeddings. And basically the lowest class embedding, the lowest Euclidean distance is then taken to be Clip's prediction or the model's prediction for this particular test image. Now, when comparing these approaches, we found that the few-shot approach is actually most effective at reducing the accuracy gap between the non-disability and disability objects. So as we just calling back the results from the previous section, the accuracy gap in the zero-shot setting was around 17%. But we were able to reduce this right down to around 2% when we use a few-shot approach. And this is more successful than either of the LLM augmented approaches. And so this really hints, I think, at something promising. You know, perhaps we can make models more equitable by simply providing them or adapting them on a few images of rare concepts. So this is kind of similar to the in-context learning we've seen being very successful with LLMs. But unfortunately, things are not as clear-cut as that. These numbers in the first column were presented or tested for simple images, simple test images. But when we move to more cluttered real-world images, which show not just the object, but kind of other stuff in the background, the accuracy gap is reduced to a much lesser degree, so only around 14 percentage points. And you may say, okay, well, maybe just increasing the number of few shots that you provide will improve things. But our results showed that this was not the case. So specifically, we tested a 5-shot, 10-shot, 20, and 40-shot setting. And we see that in the simple images, which are these light blue bars, that using just even 5 shots is enough to bring that accuracy gap right down from, you know, as I said, 17% to around 2%. But in these more cluttered, complex images, so these are these dark blue bars, we see that 5 shots does reduce the accuracy gap a bit, so from around 25% to around 14%. But then it kind of just sits there, even as we increase the number of shots. And so I think while a few-shot approach holds promise, I think there are still some open questions in how we get it to work reliably in more complex real-world scenarios. So yeah, that was a lot of information thrown at you in a short space of time. It's indeed an exciting time in AI, and I think there is real opportunity for generative AI to bring technological innovation to marginalized communities, but I think there is still a lot of work that needs to be done to do so successfully. And so I wanted to close with just a few open questions that our team is currently thinking quite deeply about in how we choose to drive this work forwards. And if any of these questions resonate with you, then please feel free to reach out to me for a chat. I'd love to learn more about how you're thinking about these problems. So the first question is, how far can we push this few-shot approach as a mitigation strategy? So we saw, as we saw in the earlier slides, some promising results in how they can reduce the accuracy gap between disability and non-disability objects. But how can we make this a guaranteed solution in all scenarios? How much data, some of the questions that come with this question are, how much data do we need to actually give these models to learn a long-tailed or a rare concept? How do we adapt these models in a computationally efficient manner, especially because they're so huge? And then, of course, the wide set of social science questions that come with this. How do we even collect data that represents these rare concepts? Do we collect it from the communities themselves? Who owns that data? Where does that data get stored? And so lots of complex socio-technical questions there. Second is, how do these strategies, do these strategies extend to other marginalized communities? Obviously, in this talk, I focused a lot on results for the blind and low vision community. But our current work is looking at how well do these strategies extend to other marginalized communities, and we're specifically partnering with the MSR Africa Lab in Nairobi, as well as the MSR India Lab in Bangalore to help explore these questions. And then finally, our team is also interested in if there is this risk of compounding bias for marginalized communities if we use these models as evaluators. So our work showed that CLIP obviously has its own performance disparities, and when we put CLIP in a downstream model, there are also performance disparities there. But what I didn't mention is that CLIP is also very widely used to evaluate other models and also to annotate and filter data sets, typically through something like a CLIP score. And CLIP is, of course, not the only model being used as an evaluator. We're now kind of seeing LLMs ubiquitously being used to evaluate other models. And so we're really interested in understanding if there might be this kind of compounding bias in these circumstances. You can imagine that if we have a biased model or a model that doesn't know, doesn't know things about a particular class of content, and we're treating that as the gold standard and measuring other models against it, then we could be instigating this kind of cycle of making models kind of worse and worse for people in the tails of the user distribution. So I think, just something that we're thinking quite deeply about. So with that, I'll leave you that sort of open questions. They're not easy questions for sure. But I'd like to thank all the people behind this work, and thank you for joining the workshop and for listening. We now should have a little bit of time for some questions.